Good day, everyone. It is now time for the fifth and final podcast of week 2. And this one is on redox titrations. Titration should ring a bit of a bell from Chem 20 at the very end of Chemistry 20. A lot of time is spent on titrations. And ultimately, a titration involves when the concentration of one solution is determined. By quantitatively, that means going through numbers, observing the reaction with a different standard solution. And standard solution, by definition, is just a solution where you know the concentration of it. Ideally, we would have been doing a lab this week if we'd been in school. However, reality is that labs are a tough thing to do in any sort of quality from distance learning, but I still want to make sure that we're talking about the concepts related to titrations. It's an important one. Okay, go back to the parts. Now on your notes, these are empty and I filled them in on the PDF. But please do go back, think about what's what, remember the terminology. The burette is the actual piece of glassware. And again, this should be familiar to you from last year. The titrant is the liquid that's in there, right? So that's the solution that's inside of the burette. Erlenmeyer flask is what you see on the bottom here. And inside the Erlenmeyer flask, the solution that's in here is called the aliquot. And that would have been a term that you learned last year as well. Now, the other three are simply pieces of equipment. The burette clamp that holds the burette to the retort stand. The valve is called the stopcock valve. It's what we can very carefully control the amount of titrant that's leaving the burette. All right, piece by piece, let's look at an actual setup. This should look a little bit more familiar to you from last year. And the substance that's sitting inside of the burette here, the titrant, this is the KMNO4 solution of that, which has a lovely purple look to it, potassium permanganate. And what we have down here that the titrant is flowing into is a solution of iron 2 sulfate, just to put it into context. And essentially what would happen as the titrant goes into the Erlenmeyer flask, we start to see a color change, and eventually that color change will become permanent. At the point at which the color change becomes permanent, we say that we have a quantitative reaction where we're able to actually use the known standardized concentration of the one solution to calculate by stoichiometry the concentration of the other one. Okay. Just to remind you of a couple things when it comes to redox titrations, some pretty common chemicals that you'll see are the ones that I was just showing you before, that nice purple one that has that permanganate in it. And the other one that's pretty common is dichromate. And the reason why we use them so much is twofold. They're really quite strong oxidizing agent, which means that they react with almost any reducing agent, which is pretty helpful. The other really useful thing about both of those OAs is they have obvious color changes, and color changes are important in titration. That's how we see endpoints. Endpoints are when we have added enough volume of the titrant to completely react with the given amount of the aliquot. Okay, so color change perspective, I just put these up here so you could see them a little more clearly. Now, the permanganate here that would go from purple, pink to colorless is what you see here, right? So as the permanganate reacts, it goes colorless. Vice versa, the alternative one where we take that dichromate, as dichromate changes into the chromium 3 plus ion, it goes from that orangey yellow into quite a nice distinctive green, okay? Just so you're aware of why these are chosen and how useful they are. So remember, distinctive color changes and both strong oxidizing agents. Super useful. Okay, look at the table that we've got here. This is the example that's in your notes, and this should look somewhat familiar from last year. Now, a couple reminders to you. When you see something in square brackets like that, it's actually telling you what the question is asking. Square brackets are related to concentration. So the whole purpose of this problem is to figure out the concentration of the MnO4 negative, the permanganate. And there's a lot of information too that's always in the titles with titrations. So pay close attention to them. For example, we're given a volume, we're given a concentration of our C2O42 negative, and then we're told the second thing that's there, acidified permanganate. Now, remember what I've mentioned to you before. As soon as you see the language that something is acidified, then you know that H plus is going to be an option to use and liquid water is an option to use. Okay? Keep in mind as well, if we are titrating a given volume, then this given volume is your aliquot. That's what's sitting in the Erlenmeyer flask. Vice versa, it is this acidified permanganate that is the titrant. That's what's sitting in the burette that is drip, drip, dripping down. Okay, first step here is we need to figure out the volume of titrant added. So a reminder of how to do that is we take that final burette volume and we subtract the initial burette volume, and that'll give us the actual volume of the titrant added. So subtract those. Because we're doing subtraction and these are all to the 100th spot, our answer should be to the 100th spot as well. That first one, 15.60. The next one, you subtract them, 14.65. And the fourth one, 14.55. And the last one, 14.60. And again, to do that, I would have taken, for instance, for trial number 4, would have done 23.25 minus 8.65 and gotten 14.60. Now going back to Chem 20, there's 4 results there, but we need a minimum of what's called 3 concordant results. And I'm not going to be able to write this down very easily on here, but it's on your notes. Concordant results. And 3 concordant volumes are 3 volumes that are within 0.2 mils of each other. Now, don't get me wrong. If there's 4 volumes, 5 volumes within 0.2, that's all the better. It just means your results are even more accurate. But at minimum, at the least, we've got to have those 3 concordant results. In this case, and we've got them, 14.65, 14.55, and 14.60. This one's not helpful. It's not concordant. So our next step then, in order to figure out the actual volume of titrant, of that acidified permanganate, we need to get the average. So we say V average is equal to, and add them all together, averages are nothing new, 14.65 plus 14.55 plus 14.60, all of those are mils. I did have 3 concordant ones, so I'm dividing that whole thing by 3. And my VAV, which is still going to be to the 100th place, is 14.60 mils. This is the volume of permanganate. Okay. Chart's been figured out. Our next step is to do the stoichiometry to actually get to our goal. What is the concentration of that permanganate? So moving on to the next page, I gave you in your notes an unbalanced reaction for this equation. Now, look carefully at it. It's unbalanced and everything is laid out there, including the H plus and H2O. It's an acidified solution. So I need to stop and look at this and pull out my oxidation numbers so that I can balance it. Applications. Go with the easy ones first, those common numbers. So -2 for the oxygen, -2. My hydrogen here is a +1. My manganese ion is a +2. I've got my -2 again for oxygen, +1, -2. Easy ones are finished. Keep going. Go back to manganese. 4 times -2 is -8, but I need -1 total, so I'm going to add 7, because +7 plus -8 is indeed -1. This one over here, I've got 4 times -2, which again is -8, but I need -2 left over, so that's going to be +6, which has to be split into 2. Each carbon is +3. If that's not clicking for you, it's because you need to write out more work. No big deal, but just take the time to do it. Over to carbon dioxide being produced, 2 times -2 is -4. I balance that out with my +4 on a carbon. Checking out what's happening here, look for numbers that change. Manganese is going from a +7 to a +2. It's going from a higher number to a lower, which means it is gaining electrons. How many electrons does it gain? Well, from +7 to +2, it's going to gain 5 electrons. In other words, this is a reduction reaction. Okay, keep on going, have a look, and we jump to what our carbon is doing. Carbon is going from +3 to a +4. Now, +3 to a +4 means that it lost an electron, just one, so lose 1 electron. Now be careful, that's 1 electron per an atom, but I've got 2 carbon atoms there that are reacting, right? Don't lose sight of that. 2 of them are reacting. So I'm going to have to take that and times by the 2 atoms that are there, which means we actually have a total of 2 electrons being lost. This, because we're losing electrons, is oxidation. All right. Look at what we have. A gain of 5 electrons, a loss of 2 electrons. Definitely unbalanced, so next step is to balance those out. We're going to get to the lowest common number that they both go into, which is 10. So times the 5 by 2 to get to my 10 electrons gained. Vice versa, take this 2, times it by 5 to get to my 10 electrons lost. We're at that lovely point where I'm going to end up being able to balance these. But I'm going to have to multiply my oxidizing agent, my permanganate, by 2. Vice versa, I'm going to have to multiply my reducing agent that undergoes oxidation by 5, right? Don't lose sight of what's going to happen at the front of each of those. Okay, I'm going to go to the next page to actually write down the balanced reaction of this. So moving on to this one, we have a total of, because remember I said I have to multiply by it, 2 MnO4 negative aqueous, which is going to be added to, this is where we had to multiply again, 5 C2O4, 2 negative aqueous. Now, some number of hydrogens is going to have to be added to this, so leave room to put that coefficient. Produces. Now, if I have 2 manganese going in, I'm going to have 2 Mn2 plus aqueous coming out. And we have our carbon dioxide, but pay attention. If 5 times 2, which means 10 carbons are on this side, then I'm going to have to make sure that I have a total of 10 carbons being produced. Last step there is the water. I don't know how many yet. We'll play with that in a second. Okay, go to oxygens at this point. My total number of oxygens on the left-hand side here, I've got quite a few. We've got 5 times 4, which is 20 oxygens, plus 2 times 4, which is going to be another 8 oxygens. So we've got 28 total, okay? 28 reacting. Go over to the right-hand side. 10 times 2, there's 20 oxygens in the carbon dioxide, which means I'm going to need 8 more to make 28 totally being produced. Check out the hydrogens. We have a total of 16 hydrogens, 8 times 2 being produced, which means I'm going to have to put a 16 on this side in order to have an accurate amount reacting. So there's our coefficients, 2, 5, 16, 2, 10, and 8. Moving on to the lovely stoichiometry. Look back to your information and what you have. Remember that V average that you figured out for the permanganate goes under the permanganate. So V average was 14.60 mils. We can't use mils. We need it into liters, 0.01460 liters. Okay. Concentration of that one, no idea. So leave it alone. Move on to that C2O4. The C2O4, I know a lot of information about that too. We started that it said there was 10.0 milliliters that was used. So again, convert it to liters, divide by 1,000, 0.0100 liters. The concentration of that was also given in the title, 0.0227 moles per liter. Look at what you've got. If we know the volume and we know the concentration, then we have all the information needed to get the number of moles. That's key because I have a balanced chemical reaction. So if I know the moles of one, I can get the moles of any one of those reactants or any one of the products. Multiply those two together. Show your units. 0.0227 moles per liter times 0.0100 liters. We're going to get N equal to 2.27 times 10 to the negative 4 moles. Now that's N for the C2O42 negative, but I can again use the mole ratio to again get the number of moles of the MnO4 negative. How do we do that? Well, there's going to be quite a bit involved. Make sure that you think there are 5 moles of C2O42 negative for every 2 moles of MnO4. So the shortcut to figure that out is we take it and divide it by 5 and times by 2. Okay, so 2.27 times 10 to the negative 4 divided by 5 times 2, N is going to be equal to 9.08 times 10 to the negative 5 moles. Quite a small number. Okay, think about what's here. We have V and we have N. The whole goal of the question was to determine C, and you're good to go. Concentration is equal to number of moles N over volume. No problem. 9.08 times 10 to the negative 5 moles divided by the volume, remember to use liters, 0.01460 liters. Concentration, therefore, is equal to 0.006219, keeps on going, moles per liter. Okay, 3 sig digs are needed, which means we have a concentration of 6.22 times 10 to the negative 3 moles per liter. Or if you'd like, you can always convert that and say C is equal to 6.22 millimoles per liter. Both of those are equivalent to each other. Either answer is perfectly acceptable. And that, folks, is redox stoichiometry applied to titrations. Make sure you check out the PDF notes as well. Have a good day. Good luck with the assignment. You are now able to finish number 2, and that's the last bit of assignment number 2.